All right, I figured I would describe, my view on this physical question and on this topic of what's really going on in the double slit experiment. And the way I would put it is, the fact of the matter is that generally, if you have that experiment and you pour light, uh, you'd have a light bulb. And then maybe you'd have some shields and stuff, so just a little beam of the light went down some little corridor and hit those slits. In other words, it's not an ordinary idea to send one photon. One photon is weird. The scientists that say about this one photon that goes at a time, they will also tell you, if you ask them questions like, well, how long is the photon? How many wiggles of wave are there in the little photon packet? And they will tell you, oh, well, it's not really like that. You can't really say its length and stuff, because there's an abstraction there. The photon is the weird phenomenon. What's really going on as far as why we think there's a photon and it's spatially located, very good reason, don't get me wrong, is because if you send it through there and you have a detector that detects just one photon at a time, you get one little speck. Um, but I even put it wrong that way. Detects one photon at a time. No. If you have a screen with it's an array of detectors. Each little pixel of the detector, it's like it could get excited by electromagnetic wave that hits it. And the reason we say there's a photon is because it seems possible that just one little speck get hit at a time. It's not like a whole wavefront and a whole row of them go off at once. In some cases. But in the general case, like I say, with a light bulb where there's multiple of these photons where light waves are going out, you just have, wave behavior. Absolutely wave behavior with refraction, diffraction. These are all wave phenomena, terms from wave mechanics, not quantum wave mechanics, just, water waves, sound wave, the waves that we were dealing with in the early days of science. Waves are just as natural as particles. They're just as intuitive that they exist, that there's something happening there. And some phenomena, appeared to be wave phenomena to begin with. Now, light, it wasn't necessarily as obvious, but in the lab it became obvious pretty quickly because, the fact that different wavelengths reflect different in glass, you know, you wouldn't expect that. If a particle hits something, and some go in and some bounce off, the angle they bounce off will be the same, right? If you hit them with less power, less will go through. No, but with a wave, they all go through partially and they're reflected partially. And how much they're bent depends on their wavelength. And that's the kind of phenomena you see with light. So forget the slits for a second. Let's just say you have a simple optical thing where there's a crystal, a triangular crystal. So, like, there's some gloss to the surface. That means some of the light bounces off and some of it goes through. And there's two detectors. And when you turn on the light shows up. You have a light that's brightness, 1 light power. Then each of those is going to be half that because half the light gets bounced this way and half of it goes through the other way. Now, the weird thing is when you turn this way down, and in order to do this, you actually have to have a laser. So it brings in like, well, what is the laser really? But let's just pretend you turn the regular light down until it has just a little bit enough energy so that this one photon is going off at a time. So it's going dink or it's going dink. Yeah, that's the weird part. Now, why do you have this photon? Well, I would assume because the light is a wave-like phenomena. So, when you have an electrical current in a radio tower, the the light, the invisible, radio frequency electromagnetic radiation, it goes off in a ripple, actually a spherical ripple, you know, from the tower. Now, why does it appear like, oh, it's one photon at a time? It's a whole cloud of these photons, not like a regular wavefront, but like that's because of the quantization of energy that Planck discovered, which it's like quantization of energy or space or mass or whatever. Things are in these tiny little units. Ultimately, it's like space is in tiny little units, which is makes sense that a particle is the fabric of space, um, because there's these little, space is pixelated. It's not a classical pixel. It's stretchable and stuff in the sense of space and time distortion can do weird things to it. So it's not as discrete as a rigid grid structure like the pixels on a video screen, but it is pixelated in the sense that you're going to have like aliasing effects. Like if you only have 256 colors and you have a picture, you're going to have those jagged edges of break from where your gradient has to choose this color or the one next to it, and you get these jagged aliasing effects. And it would appear to me that the concept of a photon is some sort of an aliasing effect. It's a glitch that when you're at such low energy, when you look at the really low energy phenomena of it, because of the partitioning of, subnanoscopic space, you get these aliasing effects where the wave is so weak it can just make one little jagged over here. Normally, a normal amount of light, the photons go out and half go that way, half go that way. There's wave fronts, cancellation, interference, all the regular wave stuff. And so it looks like, light is definitely waves. And the weird thing is just like, well, when you turn the power way down, so far down that you get that you're interacting with this quantized pixelization of all of our fundamental space time and mass quantities, all the measurable quantities, that you get this weird effect. The other thing, though, of course, is that particles are acting as waves. So that makes them look like waves, though generally they look like particles most of the time. Somehow there's a concentration of energy. And that seems to be just because when you have such a high frequency wave, is so compact that it looks and acts like a particle. Um, and yet fundamentally, you're obviously looking at the same phenomena, that billions of electrons look like waves, but with a really short wavelength. And one electron, you can evoke this little pattern that shows you that it also is rippling out in circles. But its interaction with the space around it causes it to have an effect, have this little anti-aliasing impact, and and such that becomes its normal behavior. But with lights, obviously, it's waves. There's a weirdness when you turn the power down so much that you're impacting the basic quantized nature of the medium and the energy. And so that's what it remains to be explained. Whether light is a wave or not, how is it going through? I mean, a wave goes through that apparatus, hits the reflector. Some of it bounces, some of it goes through. That's always the case. When you turn the power down, you have evidence that that's still going on, but just one little light flicks up here or here. Well, whatever. That's a different phenomena from the fact that the basic wave mechanics is going on. And that weirdness will have more to do with either the medium, the nature of the medium, as we explain why does it appear to be the case, the medium that it's in, or some dimensional idea where, in a higher dimensional space, that ripple is actually, it's still local to itself. So, and that's why it appears coordinated, such that it can make a speck on this detector or a speck on this detector, but never both. So, yeah, I just figured I'd put that out before I go watch Game of Thrones.